All righty. Good morning, everybody. It is our second week of all online instruction. So we'll go ahead and get started with the announcements for today. I have some repeat announcements just to reiterate and make sure we're all on the same page, and some new announcements. So for the first point, this is repeat from Friday. The practice exam is open and has been open since the 25th of March, and it'll remain open until exam 2 starts. Review session is still during our regular lecture time, and that will be led by TA Felipe. As you may have received already, my note via Carmen announcements that proctorial remote proctoring will be disabled for exam 2. So this will purely rely on the honor code, as it has always been anyway. Also in the March 28th announcement is that the length of the exam has been increased from our usual 55-minute quote unquote in-class length. And that's been doubled to 110 minutes. The number of questions remain the same. But you just get twice the length of time to complete your exam. And you still have the same 24-hour window to start your exam continuously for 110 minutes. So very similar to exam 1, it's just you now have extra time. I should also note, if you review the exam 2 guide and resources, that you'll need to upload your note sheet within 24 hours of the closing of the exam. And we'll send out a reminder. This is 5% of, 5 points of your exam. So treat it like 5 points and just upload your note sheet how you've done it, for exam 1. And once again, Dean David Williams has sent an email along with some other emails that you've received from the College of Engineering about pass no pass. Continue to discuss that with your undergraduate advisor. So that's a repeat from last time. Okay, with that, let us continue. All right, so this is where we left off last time, where we were talking about trends in magnetic properties for the different types of magnetic materials. So to recap, you can have diamagnetic materials, paramagnetic materials, ferromagnetic materials, ferrimagnetic materials, and antiferromagnetic materials. And of course, they have different trends in terms of their susceptibility or a material's ability to become magnetized. So before we continue on to domains in ferromagnetic and ferrimagnetic materials, as promised, I will go over example 1, and that's what I skipped last time. So we'll go over that to talk about some of the concepts that we already talked about in terms of magnetic flux density and in a magnetic field. Okay, so before we talk about the response of a material with an applied magnetic field here and what's happening at the atomic level, at the domain level, let's go back and crunch some numbers. So let's go back to that. So here you have a material, my favorite material, my favorite fictitious material, vibranium, and it has a magnetic flux density of, some bar of this material. Obviously, you can also treat this as let's say a bar of, iron or something like that. But the whole point is this is a general strategy. And it has a magnetic flux density, or B, of 0.63 Tesla at an applied magnetic field of 5 × 10⁵ amp per meter. And so what is the magnetic permeability and magnetic susceptibility of this material, right? So these are values that give us an indication of how easy it is to magnetize a material. So we know the relationship between the magnetic flux density and the magnetic field, H, is they're related by the magnetic permeability, or mu. And so we arrange this, we get magnetic flux density divided by the magnetic field will give us a permeability. So we know that the magnetic flux density is 0.63 Tesla at an applied magnetic field of 5 × 10⁵ amp turns per meter. And that will give us a value of 1.26 × 10⁻⁶ Henry per meter. The second part is, what is the magnetic susceptibility of this material? Well, we know the magnetic susceptibility, chi sub m, is related to the relative permeability of a material minus 1. And so we can normalize the magnetic permeability of a material relative to that of permeability in free space minus 1. Okay. So that gets us, we just calculated the permeability as 1.26 × 10⁻⁶ Henries per meter. Permeability of free space is, or in vacuum, is 1.257 × 10⁻⁶. So that ratio, minus 1, is equal to 2.387 × 10⁻⁻3. So this tells us that it's larger than the magnetic susceptibility of, let's say, diamagnetic materials and paramagnetic materials, which tend to be more on the order of 10⁻⁵, 10⁻⁶. So it's a little bit higher than that. Okay, so somewhat of a strong magnet, but not as strong as, let's say, ferromagnets. I'm going to pause here so that people can take a look at the screen and also have some time to write down some of these numbers. And while you're doing that, I'll talk about one of the questions that I received and that Tony pointed out last time from the lecture. And so one of the questions was, when we're dealing with descriptions of magnetism, one of the examples that I gave was, an antiferromagnetic material, manganese oxide. So let's go to that. See. Yeah. So here I gave an example of manganese oxide, in which these magnetic centers, the manganese 2+, the spins, the magnetic dipole here can be a spin up, spin down. And so how do they talk with one another, right? And that's through the indirect or super exchange, where the DZ orbital of, let's say, manganese 2+, DZ squared, will overlap with the 2PZ orbital of oxygen. Let's write that a little bit more clearly, right? So here's another DZ squared. And I said, if this is spin up, this is spin down, this is spin up, this is then spin down. And so they can exchange information with each other that way. The atoms can actually communicate through just the orbital bonding and this and spin occupancy in those orbitals. So then one of the questions was, is there a size dependence to this sort of description? What happens when you go down to a molecular level versus, infinite solids like these examples that you see here? The short answer is You can still use these descriptors, right? Orbital bonding, and how the spins are aligned and occupied within these within the orbitals. That holds true for molecules as well, right? So if you have, let's say, ferritin, which is a biomaterial and has all these, let's say there's an iron center and there's a bunch of, this is my version of alpha helices. This, the iron center, you can treat that, and you can also describe it in the same way, and it can be magnetic. There are other, biomaterials, biological examples out there in which you can treat, even though these are, globular examples of the alpha helices surrounding the metal center. You can isolate that metal center and talk about its magnetic dipole in a similar way as you would when you're discussing periodic, infinite solids. The other example in terms of finite size effects is when you come across nanomaterials. And so there, when you talk about coercivity, and this I think is probably more pointed towards the question, in answering the question, is it, to a certain extent, as you decrease the size of a material, from like an infinite solid, and you decrease the size where you get, let's say, a nanomaterial, you can have alignments within within that material. So what do I mean by that? So when you talk about coercivity, right? How big of a magnetic field do you have to apply to get the magnetization to zero? Can you use that same terminology? The answer is yes, but at some point you're making the material so small, right, that it's actually smaller than the average domain size in a regular bulk solid. There, then you have to talk about surface effects that dominate the nanomaterial that you wouldn't have in a regular bulk material, right? So there are surface energies that you have to take into account that also is a push and pull when it comes to dictating the observed magnetism that you see in the material. So we'll get to that in the materials, nanomaterials module in just a little bit. So the short answer is yes, we can still use the same formalism and the same terminology to talk about magnetism in molecular systems as well as in nanomaterials, where the particles are quite small, smaller than the grain sizes that you typically deal with. And so for different materials, where the critical size is for these nanomaterials, that is different from system to system. So we'll talk about that in a little bit, but that is the short answer. Yes-ish. Okay, so I'm going to pause right here to look at the chat, and if Tony or Janet can unmute themselves and let me know what the top questions are, I can start to tackle them.
Yeah, if you could just please go back to the slide where you had written out the example on and walk through the unit analysis associated with that, that would be great, please.
Yeah. Okay, so here, let me go back. Right. So we know that magnetic flux density is in the units of Tesla. And I think that's probably more for the first part and not for the second part, right? Because the units cancel out basically.
Probably, but that was not specified. Somebody just asked to walk through the units.
Oh, okay, sure. Yeah, so when you have Tesla, right? So Tesla is also, Tesla, here, let me wrote that down. So Tesla is just, so if you go back, this is also covered in your, let's see. Yeah. So Tesla is just Henry per meter times amp hours per meter. And so when you divide that by the applied magnetic field, you end up with henries per meter. Does that make sense? This is just all unit conversion. And that, let me look it up to see which one it is. Yeah, so if you look at table 18.1, it has a summary of all the magnetic units and conversion factors between standard units, so SI units, as well as what's called the CGS EMU system. Obviously, we're sticking to the SI unit system where magnetic flux density is written in Tesla. So B is in Tesla, magnetic field strength is in amp per meter. Magnetization is also amp per meter. Permeability is Henry per meter. And of course, relative permeability and susceptibility are unitless because they're ratios. All right, let us continue. In terms of when we talk about domains, so now this goes back to the question of size. When we talk about domains, what's actually happening at the atomic level and in terms of the alignment within the grains of the material. So here you could see if we don't have any, for this particular material, if we don't have, for ferro and ferrimagnetic materials, there's already some alignment, right? As opposed to, let's say, a paramagnetic material where the random alignments sort of cancel each other out. As here, if you don't have an applied magnetic field, that's H equals 0, the grains can be aligned like this. There's going to be, for ferro and ferrimagnetic materials, there's going to be some net alignment. As you increase the magnetic field, you can start to see that, let's say this is the direction of the alignment. At some point, you're still sort of, there isn't going to be an overall net alignment, well, there is, but it's not as strong. And then as you increase the magnetic field some more in the same direction, what you see is then there's going to be a growth of some directions and then decrease in the magnetic dipoles in other grains. And then at some point, the fields that start to be more aligned with the applied magnetic field will grow at the expense of the poorly aligned ones, right? They all start to align. And so the grains that are already mostly aligned with that will start to, will grow, and those grains get bigger, whereas the ones that are not aligned will then will then decrease. And eventually you'll have some net magnetization in some direction. And at the saturation point here, your entire material will be aligned, right? So what's happening here? What's happening is that it's going to be, these grains are gonna have to change sizes, right? And so what's happening is the domain wall. So within your material, you have all of these domain walls that separate the domains, the magnetic domains within each grain. And so as you apply your magnetic field and it gets higher and higher, it can override that and flip the magnetic dipoles. And so these are the domains that you see here. So here you can see, alignment this way, and you can see that there are these domain walls and they have some sort of energy. So for you to flip all your spins, that takes quite a bit of energy. So we talked about magnetic dependence in terms of the saturation, magnetization. It can also be temperature dependent, right? As we increase the temperature here, what we talked about before is that, you can have, in thermal conductivity, you can have atomic vibration. So you can have phonons that will increase as the temperature is increasing. But this is actually counter effective to maintaining the magnetism in your material, because as these atoms are vibrating, as the phonons are increasing in energy, it'll actually destroy the magnetic moments. Because before, let's say your spin in ferromagnetic materials, your spins were, within a grain were aligned. But now as atoms are, you have atomic vibrations that are increasing, they'll actually destroy that alignment. And we've seen that with the iron wire demo, whereas, Janet was increasing the temperature in that demonstration at 770 degrees C for iron, you saw that the magnet dropped from the wire. So it lost its magnetism, and we called that the Curie temperature. That's a critical temperature from which you'll have alignment, magnetic ordering, and then you lose the magnetic ordering. And so that's captured here in this plot where you have saturation magnetism as a function of temperature. So it actually decreases at, and you see here at 770 for iron, that's when you lose the magnetization. If you were to plot this in terms of chi, the magnetic susceptibility, as a function of temperature, we would see that where, the susceptibility decreases, so a material's ability to magnetize decreases, and then, basically peter out. And this here is the Curie temperature, right? That's the critical transition temperature in which a material will lose its magnetization and magnetic ordering. And of course, that's different for different materials, right? So here's another example for iron oxide. So it's the loss in magnetic ordering occurs at a lower temperature. So basically here below TC, you have some sort of ordering, and above TC, you're going to have, basically random arrows because it's lost its magnetic ordering. So let's look at the BH magnetization curve again, where we can say at the beginning, there's a materials property, what's called the initial permeability. So right where H is very close to 0, we can take this instantaneous slope, and that gives us a sense of whether or not a material is going to be soft or hard, just looking at this curve. And so soft materials tend to have a much higher initial permeability, whereas hard materials tend to have a lower initial permeability. But that will change as you increase the magnetic response, the magnetization response will change as you apply the magnetic field. Right, and so with increasing H, domain sizes grow, and then at saturation, your magnetic saturation is reached at a very high field strength, and this has the lowest permeability. So if you're looking at the slope of this material, the slope of this curve, you'll see that you'll start off with some initial permeability, that slope gets higher, and then it peters out as you increase the magnetic domain, the magnetic field. So why is there a hysteresis? Why isn't it that as you increase, the magnetic field, you'll also come down along the same path? And there's what's called a hysteresis. So there's a memory effect. There's a magnetic hysteresis in the material. So what happens is as you initially increase the magnetic field, when you come back down, it doesn't come back down along this curve. It actually comes back down along this curve, because once you've saturated, as now you're applying a reverse magnetic field to bring down the magnetization in the material, there's what's called, this is the remanence or the residual magnetization. So what that means is all the grains in your material, when you apply a reverse magnetic field, they're not all going to relax and decrease at the same time. There's going to be some grains that have magnetization, that still experiences when you had reached magnetic saturation. So it just means there's an unevenness in the magnetic response. And so we can quantify that unevenness by the residual magnetization or the remnants. And so that's often referred to as the B sub R. And then if you then keep applying the magnetic field, but in the negative direction, in the opposite direction, negative is just, you know, relative. At some point, you'll know how much of a magnetic field do I have to apply to get the magnetization back down to 0. And so that's known as the coercivity, or H sub C, right? In this BH curve. And then you have some symmetric response here. You have some symmetric response here where you reach magnetic saturation, but for a magnetic field that's applied in the opposite direction. And then you can come back up, get the same value here, should be symmetric. And then you can come back up to magnetic saturation. And so this is what it looks like at the atomic level with your spins, where you induce a field, you're going to align it. So if this is your applied magnetic field, the magnetization that you experience will respond to that. And then as you decrease the magnetic field, the saturation, the magnetization in your material, now you'll start to see that some grains will start to follow that, but the majority will still have, you know, some residual magnetization. And then when magnetization is 0, your grains will look something like this, where there isn't any alignment anymore. And then you apply a magnetic field in the opposite direction, and then all the spins in your material will align in that direction. Okay. So I see a question: does the same response apply if you haven't reached magnetic saturation? Yes. So all that means is if you haven't reached magnetic saturation, then you're probably stuck somewhere in the middle, right? I mean, if let's say you go up here, that just means you haven't reached this response just yet. So yeah, potentially you could have some impartial, you know, maybe most of it is aligned, but let's say you have a small grain that could still be like this. Sure, that's all it means, you
know. We have a couple other questions as well.
Okay. Sure.
On slide 14, there's one that says, "Why is the magnetic moment 4?" Are these net spin moments constant for every cation, or will it differ? And are the numbers that are given, or are the numbers given, or the numbers that you miscalculate? So why is it 4 for the magnetic moment, and would they have to calculate it?
Yes. So it's just dependent on the number of unpaired spins. So for different magnetic centers, so you know where there are unpaired spins. Yeah. So for iron here, this is just iron 0, right? Or let's say chromium, you have, if this is just chromium 0, you have what's called, when we went over electron configuration in module 2, we said that chromium is actually a special case where it's 4s instead of 4s2 3d4. It's actually, it wants to have half filled orbitals to be more symmetric, energetically favorable. It looks something like this: 4s1 3d5, right? So while the question is not specifically for chromium, I thought I pointed out anyway. So if it's 3d5, when you look at the electronic structure of the 3d orbitals, you could say, okay, well, I could just not pair up with anybody, and I could just be by myself and have 5 unpaired spins. So that's for chromium. And that also applies for manganese, iron, cobalt, nickel, copper. Now, when we talk about optical properties in the next module, which will come up later in a little bit, we'll need to discuss how actually these 3D orbitals don't actually all sit at the same energy level. It depends on what they're surrounded by, what's called their ligands, right? So let me go back to this example where you could see here, manganese is surrounded by oxygen. Here's some iron when we talk about octahedral versus tetrahedral oxygen. When we say that, right, we mean octahedral. So there are 4 oxygen in a plane. These are axial. So this oxygen, the iron 2+ octahedral, let's take that example. So this is in plane and this is out of plane. So that makes, all right, so that's the 3D version of an 8-sided polygon, hence an octahedron. And so when that happens, what's happening is the ligands in the axial, so the oxygen in the axial direction will cause an energy split versus how iron is bonded, you know, in the in plane like this. So what you actually will see, this is more granular than you probably were asking about, the 5 3D transition metal orbitals like this, they'll actually split into 2 energetic terms, and that will actually explain a number of optical observations that you see, why materials are a certain color, and it's because of this. So it goes from 3D, and then where all the energy levels are the same, and then it gets split into what's called an EG orbital and a T2G orbital, and so that splitting will actually be responsible for actually magnetism and also for optical properties that you see. Now, that's way more granular, but the question asks, do you have to calculate this? Or, well, you could if you just look at the periodic table and count how many electrons there are in, let's say, the valence orbitals, okay? So, and I think there's another part. Let me take, there was another part to that question. Will it differ, and are these numbers that are given or you must calculate? It's really just a counting mechanism. That's it. So when it says, you know, there's 5 moments or 5 Bohr magneton is just given to you, right? A Bohr magneton, you can just look that up. So no, you don't actually have to calculate. You just have to know how to count how many electrons are in the system. Now, so the examples that I've given here, right, are for the metallic system or the 0 valence system where there's no charge, there's no positive charge. There are obviously examples here where there is a charge, and so you just have to know what the net spin magnetic moment are, and all these are just multiplied by the Bohr magneton that you can just look up. Okay. Let me see what else.
I had one more question.
Okay.
Or from someone. Conceptually, what does the changing slope mean for the B versus H graph?
Okay. Let's tackle that. Yeah. So your B versus H is just, right, your permeability. How conceptually, it's just how easy it is it to magnetize your material. That's it, more or less. Let's see. Okay, I think that's it for now. So we're gonna go on, and then I'll pause in a little bit as well to talk about that. Oh yeah, so I guess that's also here, permeability. Okay, let's see, we are now here. All right, so let's talk about the BH curves as it relates to different types of materials, hard materials, soft materials. For obviously different applications, you want different types of magnetic response. So if you're using read-write type of applications, you're gonna want a relatively hard material because you don't want the coercivity to be too small, right? If the coercivity, right, if these values are too small, like in a soft material, what's going to happen is your magnetic spins can actually just respond to random fluctuations, and you don't want that. You want to be able to write a spin up or a spin down in your hard disk, and you want it to stay there until your read-write head comes back along and say, okay, I'm going to need to read out this information, and then I need to flip the spin to, let's say, rewrite the information, right? So you don't want it to be too small. So hard materials tend to have large coercivities. They have low initial permeability. That's what we just discussed. They're used in permanent magnets. So here's an example where you have, let's say, tungsten or steel, where you have large coercivities. For soft materials, sometimes you do want actually easy switching, and these are more useful for like transformer applications. So the hysteresis curve is much more narrow. So the coercivity here, you could see its value, it's much smaller than that of the hard material. So you don't have to apply as big of a magnetic field. The initial permeability is quite high, as you can see here, right? It goes straight up. But it's easy to demagnetize. So here is an example where it's a commercial iron, it's 99 versus, let's say, the hard material where it's like 5,500 or 5,900 amps per meter. And when we talk about the energy that's lost due to demagnetization, we're talking about a concept that's called BH max. And so that's just the area, you know, the BH max specifically is for quadrant 2, where you say, okay, where can I get maximum energy, right? Should I be multiplying this sliver or this sliver? Well, the sliver that you want is where B times H is going to give you your max, and that's going to be the energy. So that's going to be in joules per meters cube. Okay. And then when you talk about the whole hysteresis, all you have to do is multiply that by 4, right? Because symmetrically you have area. So when you say the hysteresis energy, or the energy of the hysteresis curve, you're really talking about getting the area under the curve or within the curve, and that's going to be the energy that's lost due to, like, say, heat when you demagnetize. But BH max specifically is in relation to this quadrant 2. Okay, so here's another example where we look at different values or read off different values off of a BH curve. So here you have, you know, different values that we can read off. So for saturation flux density, the key here is the saturation, right? So we just read that off. It looks like as you increase the magnetic field, it saturates to about here, which we're going to eyeball as 1.5 Tesla. Okay. And then for saturation magnetization, that is related to the flux density as the saturation divided by the permeability of free space. And that is going to be 1.5 Tesla divided by 1.257 times 10 to the negative 6 Henry per meter. And it turns out I do not have a value calculated for that, so we're going to leave it in the analytical form. For the remnants, right, you can read that off here. So in this particular curve, it's, I mean, there's a bit of a slope. Now, if for, let me change the, you know, if you have a curve that's maybe more pronounced between the saturation flux density and the remnants, it would look something more like, you know, potentially like this. You could have a curve. Oops, that's a little bit hyperbolic. So let's do something like this. You know, so you could have something like this where, let's say, the saturation, you know, is not going to be so similar to that of the remnants value, but in this case, it is. So you read that off. So here, you know, it's basically a little bit less than 1.5 Tesla. If you had some, you know, real minor tick marks, you could say something like, oh, it's actually 1.7 Tesla or 1.45 Tesla. But in this slope, so it's a little bit less. And for the coercivity, that's where magnetization is 0. And so we'll eyeball it and say it's, you know, 17. So both here and here. So the value of the magnetic field is 17 amp per meter. And if we had to look at and say, you know, if we had to classify the what type of magnetic material this is, you know, is it a soft material? Is it a hard magnetic material? We could look at a number of values just off of this curve. So for soft materials, the magnetization, let's see how comparable it is. So let's look at here, the saturation flux density for soft magnetic materials in these iron ingot, silicon iron, permalloys, you know, they're about 1.6, 0.8, you know, they're on the order of 1 something Tesla. And so if we look at that value, we say, okay, well, that's, you know, that's about right. You know, it's about 1.5 Tesla or so. So it could be a soft material, but then when we look at the remnants for hard materials here, we can see, well, it could also be a hard magnetic material because the remnants is somewhat comparable to, let's say, sintered neodymium iron boron. So then what is it? Well, we can now look at a third parameter, the BH max. Here, that's the energy in the quadrant 2. And this is on the order of kilojoules per meters cubed. So that's actually 2,600 joules per meters cubed. So if we go back to this example and we say, okay, well, let's look at my BH max, you know, let's look at that area. If I compute that area, let's say, you know, well, I guess I could go all the way up to here. Let's look at that BH max. B max is about 1.5 Tesla, right? And the applied magnetic field is 17. So then that's about 25-ish, you know, joules per meters cube. And so the energy within the hysteresis curve is about 4 times that. So it's about 100, but that doesn't really matter because these are all in kilojoules per meter cube. So it's really not a hard magnetic material. It's probably more like a soft magnetic material would be the better classification. Okay. All right, let me take a look at some of the questions that have come up. Yeah, so is mu not provided, or can we get, yeah, so mu naught is the magnetic permeability of free space. So that is a given as 1.257 times 10 to the negative 6 Henry per meter. And then can you repeat where we read remnants from the curve? Yes. So remnants in the red curve example is right there. So that's the residual magnetization. In this curve, I read it off as, you know, something less than 1.5 because I do notice that there's a slope, but it's such a slight slope, right? So it's so slight that given that, you know, you don't have any tick marks right here, you know, could be 1.47, 1.45, that's a good estimate. Obviously on an exam, if you had to read it off, you know, it wouldn't be so macroscopic like this. You would actually have, you know, minor tick marks so you can read that off. In the green curve example, so let me just remove some of this. Oh, okay, let me just redraw that real fast. So in the green curve example, where I had saturation is a little bit more pronounced than the remnants, right? Then you could read that off of here, where your saturation magnetization is more, you can read that off as that level, let's say 1.4 Tesla, and the remnants is the residual magnetization when you don't have an applied magnetic field. So that's H equal to 0, that's more like 0.8 Tesla, right? So another question that popped up is, why is it a soft material again? Well, we looked at 3 values. We looked at the saturation magnetization. We also looked at the remnants, and then we looked at BH max. And so we had two conflicting results. One, saturation. You know, if we looked at the saturation flux density, it rivals that of soft materials, right? So 2.14 to 1.6. So that's on the order of 1.5. You know, they're on the same order. But if we look at the remnants, it's not so clear, right? Because these values are somewhat comparable. They're on the same order of magnitude, you know, 1.16. So which one is it? So then we look at another parameter for comparison, BH max. So the energy that you would lose due to heat when you demagnetize, or the area under the curve for the hysteresis curve. And there we concluded that, you know, for this particular material, it's about 25 joules per meters cube in the second quadrant for that area. So 4 times that for 4 quadrants would be about 100 joules per meters cube. But once again, we're talking about 100 joules per meters cube versus, you know, for hard materials, you're looking more like for 2.6 kilojoules. So that's 2,600. So it's not even on the same order of magnitude. So we concluded, just based on those 3 comparisons, it's more likely that it's a soft magnetic material than it is a hard magnetic material, just based on those. Okay, so I hope that answered your question. You're welcome. Yeah, okay. All right, let's move on to some examples. Magnetic storage. This is what you know and love and use every day, probably without realizing it, or you do realize it and you appreciate magnetism a lot. Right, so here in the conventional magnetic storage mechanism, you have a magnetic material, you know, here, where you have spins up, down, down, up, down, right? You have some sort of data that's there, and in order to write that, you need to apply some magnetic field to orient those grains that will then be spin up, 1, or spin down, 0. So you write in ones and zeros, right? So you can write that by applying magnetic field that aligns all the domains in the small regions of the recording medium. And then you could read it by just reading out, you know, what is that magnetization? So you can have a sensing head and a writing head. Okay. So what types of materials are used in let's say, hard disk drives versus recording tape? So they implement different types of materials. For hard disk drives, used this hard magnetic material, cobalt, chromium, and their alloys. And you could see here, so for some reason the scale bar did not, oh yeah, the scale bar did translate. Okay, so you could see here that's like 80 nanometers. So these particular grains are much smaller than that, right? I mean, they're a fraction of that 80 nanometers. So when you write, you actually write across multiple grains that then align within the write head and then the read head, right? And so you align it. Cobalt chromium happens to be hexagonally closed packed, so it's HCP. And so you'll align it along its easy axis, which is the C axis. So what happens is your basal plane AB is here, your C plane is here, and that is what gets written in hard disk drives. Now for recording tape, those literally are just tapes, and they're used more for backups. So if you've ever had a RAID system, a redundant array of inexpensive disks, well, you would have actually had hard disk drives, but they're also for massive server type of backup. There are magnetic tapes, which you can imagine could suffer from, you know, if there's a huge temperature change, you know, if it heats up a lot in a room and you don't cool your server room properly, you could lose the data within your material. But of course, that's mostly protected these days within the tape system themselves. But you could see here that the morphology is a little bit different. They're more needle-like or nanorod like. They're just made of a different material. These ferrimagnetic barium ferrite particles. So there's barium in iron oxide, and so you similarly you align as the tape goes through, and then you could read your spin up and spin down as a result of that. All right, so now we go and tie electronic properties to that of magnetism. So previous module with current module. Of course, the theory of superconductivity has been studied for a very long time now, for multiple decades. And of course, why it's of interest to us is, of course, is that it can be used in a number of applications. You probably have already heard of, the levitating trains and things like that, that uses the concept of superconductivity, where at a very low temperature in a material, there is very low resistivity within that material, and there are critical temperatures for different materials. So for copper, which is normal, it's not a superconductive material, and so as you decrease the temperature, you could see here, its electrical resistivity decreases, but then it sort of just plateaus out. For superconductive material, as you decrease the temperature, at some point there's a precipitous drop in the electrical resistivity. And so that temperature happens to be 4.2 Kelvin, which is above liquid helium temperature. So that's 4 Kelvin. So it's a little bit above that. So can we get it? So can we get this material to be cool enough to experience that? Yes, because it's right above the temperature of liquid helium. If a material is lower than that, it would be extremely difficult for us to access the superconductive properties of the material. And so the field is forever trying to find materials with high temperatures of higher critical temperatures, so that we don't have to cool it down as much. So we don't have to spend as much energy trying to cool down the material. So how does this tie in with magnetism? Well, at very low temperatures, right, the material, if it were once paramagnetic, it acts as if it's diamagnetic now. It repels, any applied magnetic field that you put onto the material up until Hc. So that's the critical magnetic field for a particular material, where the material will act as a diamagnetic material, and then up to a certain applied field, it will actually become paramagnetic again. If you increase the temperature, which goes back to this plot right here, if you increase the temperature beyond a critical temperature Tc, right, then it's no longer superconducting. And so there's a region of space in which, phase field, in which you can have superconducting properties if your temperature is not too high, if your applied current is not too high, and if your magnetic field is not too high. And so within that region, you'll have superconductivity for a material. Okay. So we can't talk about superconductivity. No, okay, before I go on, I just saw, is Hc the same as coercivity? Well, that depends. It's not. Okay, so then let's talk about the Meissner effect, where superconductors can expel the magnetic field that it experiences. So you may have seen the levitating magnet already. So let me go to that. Oh, okay, here we go. Apparently somebody's named Alan. So let me try to get, oh. I'm trying to speed this video along so that we get to the right part, but okay, well, anyway, it's going to come up or not. But basically, you may have seen this example already, where you cool down a superconductor. That's the base right here. And then you have a small little magnet, usually, it's the cube. If you buy it in a kit, it's like this little cube, iron magnet. And if you put that above the superconductor, if you cool down the superconductor enough with a liquid nitrogen, you can get it so that the magnet above the superconductor will levitate and spin, because the magnet has these field lines that will be repelled by the field lines that are in plane with a superconductor. And so what you see then is this magnet that just levitates and spins because it's rejecting all the magnetic field lines that are coming around it. And so that's the Meissner effect, where when you get a material cold enough, and then the magnetic field lines that it experiences will just go around, it will repel and it will go around that material, okay? And so what you would see in this video is that the superconductor will float above the magnet. And so I think, hold on, if I exit, I think I can actually play the video. Here we go. All right, you should be able to see the video now. So here the magnet is being placed on top of the superconductor. Here's some liquid nitrogen, that's 77 Kelvin, right? So they'll put it on top, and now it'll levitate because it's expelling the magnetic field lines, and the rotation is just the magnet, you're switching the poles, and so it's just the direction of the pole, and so it'll just continue to levitate and also rotate to repel the magnetic field lines. Okay. Right, so clearly many years of research have gone into this now. We moved on to the in the 80s, 90s, early 2000s, working on cuprates. Now there are other families that are being investigated, but the cuprates so far, yttrium, barium, copper oxide, that was the material that you saw in the example. Its critical temperature is 90 Kelvin. So when you put liquid nitrogen on top of it, liquid nitrogen is 77 Kelvin, so it cools it down below the critical temperature, and thus it can be superconducting. And so there's a lot of applications, a lot of uses for these materials. One of the challenges with using these materials, of course, is their mechanical properties. Ceramics tend to be quite brittle, and so making a lot of them and having structural integrity for a lot of the structural applications can become a challenge. But of course, people are continuously working on it, and so can you. Okay, the last example before we move on, although it is 11:17, so we'll continue with this example before we move on to optical properties for the next lecture. So sorry for running over time by 2 minutes, everybody. I'll try to stay on time for next lecture. With that, I think those are all the questions that I see on the chat. So I will see you all next time. Have a good day.